next speaker is Jeremy Levy from the University of Pittsburgh, who's in the physics department there. And if you look at his website, he also teaches general physics and has some fascinating movies. You should take a look at it. He won't have time to talk about that today. Jeremy Levy will be talking about Etch-a-Sketch. Some of you remember that. And Etch-a-Sketch Nanoelectronics.
Great honor to be here among so many fellow teachers. I'd like to talk a little bit about my research that's basically motivated by a play toy that I had as a child. Of course, now I don't play, I work, but we use very analogous tools. And actually, a lot of the research, some of the research, in fact, some of the key sparks were inspired by toys that I played with as a child. So I want to begin with an overview, starting from, the universe, and in fact, talking about the interrelationship between information and the universe. That will form a backdrop for the research that we've been working on, which is this Etch-a-Sketch Nanoelectronics, and try to motivate why we're interested, why we move in certain directions when we do research. And then I'll talk a little bit, Barbara gave a bit of an introduction. I'll also talk a little bit about how this Etch-a-Sketch Nanoelectronics might be useful for quantum computation. Okay, so what is information? Well, I think most of you are familiar with information, that information is stored in bits. Basically, all digital information is stored in sequences of ones and zeros. And there are, of course, many ways of storing information. But in fact, it was Rolf Landauer from IBM who famously stated that information is physical. What does that mean? One of the meanings of that statement is that it's not possible to extricate information from its physical embodiment. So that you cannot have the concept of information without having some physical state that represents it. There are many consequences of that. But of course, we know that there are many ways to create and store bits of information. You know, heads and tail of a coin is a bit. Okay, it's a big bit. We don't use it for computation, but we do use it for decision making, as well as the thumb, the angle of the wrist, and so forth. The presence or absence of a piece of graphite on a particular place on a piece of paper, that's a bit. Of course, the magnetic and electric dipoles form very useful and technologically relevant bits as well. And I would be remiss if I did not mention DNA, which is sort of biological information. We're all carriers of that information. That's why we exist. That's why we do most of the things that we do, is to preserve that information. Okay, so among the best bits of today, they are really those magnetic and electric dipoles, and usually there's a tension between volatility and speed. So you have, for example, DRAM on the left, the fastest but most volatile information. Turn off the power and its state goes away. You can have flash, which is slower, but it's a similar type of technology using electrons. And then you have the slower magnetic-based storage, which is non-volatile, but a lot slower. But of course, this is not a comprehensive list. In fact, there is, of course, a growing amount of research in alternative ways of storing information, as well as existing methods like Blu-ray and so forth. But again, going back to this, the concept of information, one thing that we know in physics, we learn about symmetry breaking, and in fact, it's very central to the idea of storing information. If you think about a circle, not the presence or the absence of a circle, but just the shape, it's too high symmetry to store information. If you rotate it, you get the same object. So you cannot store information with a circle. However, if you were to reduce the symmetry of that circle, turn it into an ellipse, well, now you have ways of storing a 1 and a 0. So this idea of having symmetry breaking is central, is crucial for being able to store information. You need to be able to have the ability to go between two different states. And this often happens in physics when you have phase transitions. So for example, we think about a water droplet, and we contrast that sort of nice and round and spherical. We think about all of the snowflakes that have ever fallen on the planet. Each one is different, right? And these are all distinct objects, and yet when you melt them, they all look like this one single drop. So the fact is there's an enormous capacity for storing information that comes from our physical surroundings. And one of the questions is when you look around, how do you choose how to store information? So this is, of course, we have gravitated towards certain methods using silicon and magnetism and so forth. But the question is, when they run out of steam, where do you turn? So it's not enough to be able to store information. You need to be able to process it as well. You need to be able to take those ones and zeros. This is actually whatever the back of maybe a CPU. But basically, it contains the means for taking information and transforming it from one state to another. And the central physical element of this, again, all types of logic is also by necessity physics-based. And so, unlike storage, there are fewer methods for processing information. They're basically all driven by electronics. And here's the basic element that we work with is a transistor field effect. Transistor, the idea is you have a channel that's broken here, and by putting a positive charge here, for example, you can attract electrons and close the switch. So it's a switch, basically, and by turning this gate on and off, you can control the flow of electricity. And by taking these elements and placing them in arrangements, all you need, in fact, is 4 of those kinds of transistors to make a universal logic gate, something that can, in combination of other NAND gates, so not AND gates, this is the truth table, that this sequence of 4 transistors is sufficient when multiplied out and into many billions and so forth, can do all the computations, including this presentation. So, but again, it's all based on some fundamental physics principles. So again, going back to this idea of the universe, we know that there are 4 major forces, and we believe that 3 of those 4 are, in fact, can be brought together at very high temperatures. There's this symmetry principle. With high temperatures, you have essentially one force, and then it breaks off into 3. We believe that it's the Higgs field, that is that field that then transforms into electromagnetic, strong and weak. But the idea is that that is a phase transition that leads to the richness in our universe, and that leads to information capacity. So it was Seth Lloyd who actually decided to calculate, to treat the universe as a computer, and ask the question, well, how much information is there? It turns out to be about 10 to the 90th. So not even a tenth of a nanoboogel of bits of information, on which about 10 to the 20, 120 logic operations have been performed to date. So in some sense, it's really large, but gosh, it's not even as much as Google, right? Of course, it's Google, right, which is 10 to the 100th, which is not the same as Google. So, but the point is that, yes, it's very large, but it's not infinite. And so the idea of thinking about the universe as a computer, something that's computing, at least when I think of it,